Hello, everybody, and welcome to the last lecture for Math 4400 this semester. So the topic for this final lecture is elliptic curve cryptography. So we're going to see an application of this group structure that we introduced in the lecture and in class on Tuesday. But before sort of doing anything for elliptic curves, let me just recall how the Diffie-Hellman key exchange works. So this is sort of what elliptic curve cryptography is going to be modeled after. And this was, and we had a few different types of cryptography that we talked about before. We talked about Diffie-Hellman and we talked about RSA. And so Diffie-Hellman was the one where you sent public information between two people in order to establish a shared secret. And then once you had that shared secret, you could use that shared secret to just do a shift cipher in order to transmit messages. So elliptic curve cryptography is going to be the same kind of thing. So let's recall how Diffie-Hellman worked. So first, you just had some public information that sort of everyone is available to everyone. So you had a large prime number P, and then you picked a primitive root G mod P. Okay, and that was just some information available to everybody. And so Alice and Bob want to establish a shared secret. So privately, Alice picks an integer A, and Bob picks a different integer B. And then they're going to use this and make a computation, which then gives them some data to transmit. So Alice is going to compute alpha, which is G to her secret raised to her secret number A. And Bob is going to transmit beta, which is G raised to his secret number B. Okay. Then Alice receives beta, so she knows what beta is, and she still has her secret number A. So she computes beta to A. And similarly, Bob receives alpha and then still has his secret number B, so he computes alpha to the B. And if you sort of put that all together, they've actually computed the same thing in the end. So beta to the A, this number that Alice computed, is the same as G to the B to the A, which is G to the B times A, which is G to the A times B, which is G to the A to the B, which is alpha to the B, which is the number that Bob computed. So this is a number that they were both able to compute, but it's hard for anyone else to compute it. So some of the issue is it's sort of hard to compute the logarithm that would let you bring one of these exponents down. So even though someone listening would see sort of what this number alpha was and would know what G is, even though in principle that sort of lets them determine A, there's no efficient way for them to determine A from that. So some of the point is sort of all these secret numbers are always appearing in the exponent, and that's what made this sort of made this work. And so, and another way it says is the reason this works, it's not because there's no way for someone overhearing to compute what A and B are, and then find out what the shared secret is. It's just that it's very difficult. It's very computationally complex to do that. So it sort of depends on the difficulty of the discrete logarithm problem in FP cross, which is somehow given this primitive root G, and sort of if you know some other number and you know it's some power of G, there's no efficient way to compute what that power is in F. So that X is sort of something in Z mod P minus 1Z, and there's just no sort of efficient way to compute what that is. Okay, and so that's how Diffie-Hellman works. So it depends on the difficulty of this discrete log. So the idea of elliptic curve cryptography and sort of other related key exchanges in general is that, well, there's nothing too special with this group FP cross. So we could sort of replace this group FP cross where we're doing all of our computations with any other group where it's easy to compute large multiples, or sort of in this case, large powers. So somehow it had to be easy for Alice to compute G to the A and for Bob to compute G to the B. And that'd be easy for Alice to compute beta to the A and for Bob to compute alpha to the B. These computations had to be very quick. So we need sort of to be a group where we can compute large powers easily. But it should be hard to sort of find this. So sort of you have some element G in your group, and you sort of compute some multiple of it, n times G. Okay, and then sort of someone else sort of gets just G and the multiple n times G, and they want to know what n is. It should be hard for them to sort of find what n is. So this is sort of discrete logarithm. Sort of the only difference is sort of when we're working in FP cross, so we write sort of things the group operation multiplicatively, but this is sort of just writing the group operation additively. Good. So this is what we need. We need a group where it's easy to compute large multiples, but hard to sort of undo that computation. So hard to sort of, given an element and something you know is a multiple, to sort of find which multiple it is. And then the exact same process will work to establish a shared secret. That shared secret will end up being some element of your group, and then you can sort of do whatever you want to use that as a way to like do a shift cipher once you have a shared secret. Okay. So in elliptic curve cryptography, the group you use is sort of the points on an elliptic curve over a finite field. So the general setup is you should take F to be a finite field of characteristic at least 3. So that just means so 2 is not 0 and 3 is not 0 in F. In other words, like F does not contain the field of 2 elements and F does not contain the field of 3 elements. So for example, you could take F5, like the field of 5 elements, or you could take FP for any sort of prime greater than 3. And then we have an equation of the form x cubed plus ax plus b, where our coefficients are in this finite field. That does not have we have a polynomial of the form x cubed plus ax plus b that does not have a repeated root. Okay. And so if you do this, then you can look at the solutions to the equation y squared is equal to x cubed plus ax plus b, where sort of x and y are both elements of your finite field F. And then you sort of also throw in an extra point infinity, just like we did when we were looking at sort of this kind of equation of the real numbers. And together these form a commutative group, which we write E of F, like sort of E parentheses F. Which is a little bit shocking at first, because somehow like the way we define the group structure when we were like looking like y squared is equal to x cubed plus 8 over the real numbers was very geometric. Like we sort of drew lines and took intersections and flipped about x-axis and so on. And like this description was geometric, and because it was geometric, it doesn't really make sense. Like now sort of over the field of 2 elements, like sort of what is a line over the field of 2 elements? But somehow it's okay because we saw on Tuesday in class, you could take this geometric definition and then you could literally just write down equations for the group law. So you took in the coordinates of one point and the coordinates of another point, and you sort of wrote down just a formula for the coordinates of the new point you get by adding them together. And if you go back and you look at those formulas, you'll see like starting with the coordinates, you just sort of add and multiply, you sort of add them and divide them, but you never sort of do anything else. And since you can sort of do adding and sort of dividing and multiplying in any field, these formulas work sort of just as well in this setting, where sort of your coordinates now have entries in this finite field F, and sort of A and B are in this finite field F, and so on. But everything will still work out actually very nicely, and you'll get addition laws, and they really will turn this into a group. So this is sort of some small miracle when you see it like this, but there's in actuality, there is sort of a nice way to do geometry over like a field with finitely many elements, though you just have to sort of think a lot more algebraically when you're doing it. And then you can interpret it also sort of geometrically. Good, but you get these explicit formulas, and so you get a group law, and then elliptic curve cryptography just works exactly like Diffie-Hellman, just using this new group. So the public information you start with would be the equation for elliptic curve E. So this like y squared is equal to x cubed plus ax plus b, where a and b are elements in your field F. So you have your elliptic curve, and then you have some point that lies on that elliptic curve, but sort of some x and y in F that sort of satisfies this equation in your finite field. Okay, so so your elliptic curve and the point on it are public. And then privately, again, Alice is going to pick some integer a, and Bob is going to pick some integer b. And then Alice transmits A times P, where sort of you multiply A times P. You sort of add P together A times. This is sort of using the group law on the elliptic curve. So you sort of add A together P times. Using each time the group law on the elliptic curve. And so similarly, Bob transmits B times P, which you get so by adding P together B times, but each time using the group law, adding B to itself, or P to itself B times, each time using the group law on the elliptic curve. And that gives Bob some new point beta on your elliptic curve. And then you do the same thing. Now Alice computes A times beta, and Bob computes B times alpha. So you sort of take this new points that were transmitted, and Alice computes the multiple A of one, and Bob computes multiple B of one. And just like before, this gives you a shared secret. So A times beta is the same as B times alpha. So this is what Alice computed, and this was what Bob was able to compute. And so together they get their shared secret, which is a point. So it's an element of E of F, i.e. it's a point X, Y, such in F squared, such that Y squared equals X cubed plus AX plus B. So this element that they compute using elliptic curve group law, like they get just a tuple of 2 points, a tuple of 2 numbers in this finite field F. Okay, and then sort of once they have that, well, like you would just take like the X coordinate, for example, and use that as your sort of to do a shift cipher. Like once they have the shared secret, then they can use it to sort of transmit secret messages however they want. So the trick is to sort of establish this shared secret. Okay, and so good. So this works, and just like sort of the Diffie-Hellman key exchange, where we used sort of the multiplicative group FP cross instead of the group of points on elliptic curve. It's not that it's impossible for like someone who sees alpha and knows P to extract what A is. It's just that it's difficult. It's very difficult, and it's much more difficult than it is to compute A times P. So and for Alice to like make these computations, like, well, you saw we have these explicit formulas, and they're not so bad. Like you sort of like, you could do it by hand. You can do it by hand a little bit, and certainly a computer can do it very quickly to compute multiples of things. And then in particular, you can use this sort of doubling trick. So like the method of successive squaring allows you to compute large multiples quickly using these formulas. So sort of it's no problem for Alice and Bob to like make these computations of what alpha and beta are, but it's very hard for someone intercepting it to undo this, to sort of given alpha and knowing what P is to figure out what A is. And so that's why this is also somehow a hard problem. That's why sort of the key exchange also works using this group of points on the elliptic curve. So in class on Thursday, you'll get a chance to carry out a key exchange using this curve y squared is equal to x cubed plus 8 that you worked out formulas for in class on Tuesday. And so it only, so the last thing that remains to be said is why. And so why would you want elliptic curve cryptography? We already have Diffie-Hellman. And the reason is actually pretty simple. It's just better. Elliptic curve cryptography, and somehow it takes fewer bits to make the decryption hard. So somehow you can think of this like you sort of need to work with a smaller finite field in order for sort of discrete log to sort of be difficult. So it's just the discrete log problem is somehow it's harder. We don't know as good of ways to solve it, and so because of that, you need to sort of use. You don't have to use. It's just a more efficient algorithm. You don't have to sort of use as large of finite fields. Like you don't have to be doing your computations for doing the multiplication. Don't have to be as intensive because like some simpler multiplication computations are harder to undo in this problem. So that's the reason. Great. Well, I will see you in class on Thursday. Thanks, everybody.